All right, welcome, folks. We are going to work through day 27 of remote learning, which is rational functions. So I'm going to be working through the questions that are in the handout attached, and we're going to look at rational function inequalities. So rational function inequality, just like the other types of inequalities we've looked at, compares a rational function either to a constant or to another rational function. And our general approach for solving these inequalities is going to be very similar to what we did with polynomials, where we're looking for the zeros, but now we're actually going to need to be a little bit more specific than that. We're going to need to look for wholes and for vertical asymptotes as well. And we'll then classify the areas in between each of those as being either above zero or below zero, and use that to solve the inequality. So let's jump right in. The first one on the handout is x minus 2 less than or equal to 8 over x. X minus 2, you might say, well, that's a polynomial, that's not a rational. If we put it over 1, then it's technically a rational, so we will include it. So here we have a few things to do. So the first one is always add or subtract to move things. And you might wonder, well, why can't I just deal with this by, say, multiplying both sides by x? Right? If I multiply both sides by x, that's going to simplify this down, and then I could subtract 8. So, like, here's what you don't do. X times x minus 2 less than or equal to 8. X squared minus 2x minus 8 less than or equal to 0. You might say, hey, Mr. Island, that looks perfect. Like, now I've got polynomial inequality, and we already know how to solve those, so why don't we just do that? Well, if you recall, when we looked at linear inequalities, we said one of the things that you need to be really careful about is when you're multiplying and dividing, are you multiplying and dividing by a positive number or by a negative number? And if you're multiplying and dividing by a negative number, then you have to switch the direction of the sign. Well, is x a positive number or a negative number? Yeah, we don't know. It can be both, right? X over the domain of most rational functions is going to be positive in some places and negative in others. So when we switch x over, or when we multiply both sides by x, we both need to change the sign and not change the sign at the same time. And we can't do that. So this leads us down a tricky direction. So please don't do it. This is not what we want to do. What we do want is to add or subtract when you need to move things. So I'm going to subtract 8 over x. 8 over x minus itself. So I've subtracted on both sides, and now we're going to get relative to 0. And now you might say, okay, well, this is kind of a mess. Like, it's not a nice rational function that we're used to analyzing. That's true. What we're going to do is we're going to find a common denominator. So we are going to multiply this by 1. And the 1 that we're going to multiply by is going to be in the form x over x. And x over x is never negative. No matter what real value you pick for x, you're never going to get a negative number when you do x over x. So we don't need to switch the sign here. So x over x times x minus 2. And this part is already over x, so we don't need to multiply it. And then we'll get x squared minus 2x over x minus 8 over x less than or equal to 0. And now we can push it a little farther, gather it all together, x squared minus 2x minus 8 all over x less than or equal to 0. And so now we have a rational function of the type that we're used to seeing, and we can do the analysis. So find zeros vertical asymptotes, and holes. Okay, well, to find the zeros and the holes, we're going to need the top to be factored. So I want two numbers that multiply to -8 and add to -2. So that's -4 and +2. So x minus 4, x plus 2. And on the bottom, it's already nicely factored for us with x. And so we can see as a result that the zeros of this function would be at x equals 4, x equals -2. There are no holes. And there is one vertical asymptote at x equals 0. Okay, and that's because x is the same thing as x minus 0. All right. So now we draw out our number line. We put all of these various things on it. So there's 4, there is 0, there is -2. And then we look at what happens in between each of these. Well, if you remember end behavior here, it's like what happens when you take the leading terms and divide them. So we get x squared divided by x. That is x. And so we would expect that at this end, we're going to get going up forever. At this end, we're going to get going down forever. And these are zeros, so it will actually cross right there and cross right there. And this one is a vertical asymptote. So since these zeros are degree 1, we know that the function is going to cross through at that point, and it's going to keep going up along this asymptote. Here we know that the function is going to cross through the x-axis at this point, and in order to have asymptotic behavior, it's going to have to go down. Oh, and you can't see that. My apologies. So we've plotted the zeros, 4 and -2. We've plotted the vertical asymptote at 0. And so we know end behavior is up forever to the right, down forever to the left, and we're going to have to see something like this to get our asymptote. So if we want to know which sections have this function less than or equal to 0, well, the answer is over here. So from -∞ to -2, and we include -2 because it's allowed to be equal to 0. And then we unite that with this section here, which is also less than or equal to 0. And so that's from an x value of 0 to an x value of 4. We don't include 0 because at 0 the function's undefined. It's not equal to 0, it just doesn't even exist. There's no value for the function at 0. At 4, the y value of the function is 0, so technically the function is equal to 0, so we're going to include 4, and we put our square brackets in there. And just like the other ones, you can also do this as a set. X belongs to the real numbers such that x less than or equal to -2, or 0 less than x less than or equal to 4. And you'll notice there's no less than or equal to here with the 0 because x is not allowed to be equal to 0 in the solution. It has to be greater than. All right, and we could also draw it on a number line. And in that case, we would have 4, 0, -2, and we would go from 4 down to an open circle at 0, and from a closed circle at -2 down forever. All right, so that's our first example. I'm going to stop the video there just because I'm not absolutely sure everything's working with this setup, and so please take a look at the next video in order to see the next example.